This chart has molecules. And, yeah, there are molecules moving, but we're looking at this as a piece of chart as a whole. But for here, we're just looking at
Because the electrons hold.
yes.
Oh, okay. So in a way, it is. And then what's that?
Okay. Okay. The next thing I'm going to do is a repetition of what I did. Except, yeah, so I guess it's almost a repetition. I'm not going to repeat the whole thing, but I'm going to go through a similar process. You see here how I found the change in potential energy? I'm going to now define a quantity called the potential, the electric potential. Not potential energy, but the electric potential. The words are close, they're related, but they're not the same. It's similar to, we had force and electric field. In here, we will have potential energy and potential. They're related, but they're not the same. Remember the relationship between force and field? If you place a charge Q in a field E, in an electric field E, what's the force? QE. Same thing here. If you place a charge in a potential, which I haven't talked about, a charge Q in a potential V, the potential energy would be QV. Okay. So I'm going to talk about the potential and then, so that's the next one. For potential energy, we integrated the force, right? It was the force that was integrated to get change in potential energy. For potential, we're going to integrate not the force, but the field. It's going to be the field, not the force. So let's define electric potential. Let's define. I'm going to erase here. So let's say I have a charge. So the electric potential it has the symbol V. I'll try to put bars whenever it's not clear. So V here is not volume, it's not velocity, it would be voltage. The units would be volts. It's the potential, electric potential. So let's say I have a charge here. You can assume it's a plus charge, could be a negative charge, but for starters, let's just say Q. Here's a charge Q. Let's say at this point here, called R initial, at this point here called R final. What's the potential difference between R final and R initial? What's the potential difference? So what's the definition of potential difference? So let's define it. The potential difference is equal to minus integral from R initial to R final of electric field dot. That's the definition of the electric potential. Before I find the electric potential, or actually let me find the electric potential first for a point charge, and then we can talk about the units. The units are just going to be electric field units times distance, right? Electric field times distance. So that's fine. So for a point charge, what's the electric field at distance r from a point charge? We need to know that, right? What's the electric field for a point charge? K, Q, over R squared, R hat, right? Let's say this is the R hat direction. Okay. And then dr, what's dr, this vector?
R
Huh?
R hat.
dr times r hat, right? It's a small displacement in the r hat direction. By the way, if you don't displace in the r hat direction, if you just displace around the circle, or like around the sphere, what's the dot product in that case? If, I'm saying this. Let's say I have a charge here, and I'm here versus here. I go around an angle like this, a fixed radius. What's the dot product in that case? Electric field is this way, right? Radially outward, and the displacement is tangential. So what's the dot product? It's zero. Yeah, the electric field is this way. That's the electric field, and the displacement is this way. Similar to a, if you have a mass and it's swinging like this, right? The force of tension is toward the center, right? And the displacement is along the arc. What's the work done by tension? Yeah, zero. For that reason. So similar thing. Okay. So that's why we only care about the radial direction. If you don't move in the radial direction, there is no change in the potential. Okay. So that's why we just have this r hat direction. Okay. Dot product r hat with r hat is 1. And then so you end up with kq over r squared dr. And so you have to integrate 1 over r squared. What's the integral of 1 over r squared? Negative 1 over r. There is this minus sign, becomes just 1 over r. So the overall then integral just becomes k q over r final minus k q over r initial. That's the change in potential. Let me write it this way: v final minus v initial. So this is the potential, v final, and that's v initial. So let me write down the potential for a charge at a distance, at a certain. So v as a function of r is this k q over r, which is 1 over, which is q over 4 pi epsilon pi. So again, what's the potential at infinity? Zero. And now I need to talk about units, right? For energy, we're familiar with the joule, but this would be a new unit. So the units are going to be, what are the units of V? I already said it's electric field times distance. Electric field times distance. What are the units of electric field? Newtons per coulomb, right? Times distance. What's distance? In SI is meters. What's a Newton times a meter? Newton meter, which is a joule. Yeah, it's a joule. J for joule. So it's a joule per coulomb. A joule per coulomb. So the units of V are joules per coulomb, but the joule per coulomb is called a volt. 1 volt. And I usually I would write the word volt on purpose. In the book it's italicized a little bit because it's kind of V is the quantity, the voltage. To say V is 10 volts, so it kind of seems like X equals to 10x, but it's really, this one is the quantity, this is the unit. So that's why I usually just write. So that's no confusion. So a joule per coulomb is a volt, okay? Joule per coulomb is a volt. So now, notice, what's the difference? Look at the two equations between U and V. What's the difference? Yeah, just one charge, right? There's just a charge. So let's say, notice this. I'm going to come back to the units again. So let's say I have a charge Q1 here. Here's a charge Q1, and the distance is R. What's the potential due to Q1? What's the electric potential due to Q1 at this point? KQ1 over R. Yeah, KQ over R. Since Q has a name now, it's Q1, so it's going to be KQ1 over R.
I will.
Yes.
I might have missed this, so it just might be a definition, but how come we can say that the change in electric potential is equal to that in
Definition.
just definition?
Yeah.
Okay.
Yes, and the minus sign is actually not to make life hard, it's actually to make life easy. As you saw earlier, with the minus sign for potential energy, it made the law of conservation energy look nice. Because kinetic at the beginning, plus potential at the beginning, ended with plus signs at the end. So that's the potential, that's the electric potential due to Q1, right? Right? You see, this is the result we got. So the next thing I want to ask you this. Let's say I place a charge Q2 right here. Here is a charge Q2. What's the potential energy between the two charges? U1, 2. What's the potential energy between these two charges? Yeah, it is K, U1, U2 over R, right? What's this? KQ1 over R. Yeah, this is V1, right? So it will just become Q2 times V1. Q2 times V1. So the potential energy, so once you know the potential, and you place a charge in that potential, the potential energy is just the product of that charge and the potential. Just like when you have the electric field, and you put a charge in an electric field, the force is QE, right? The charge times the electric field. Similar thing. Yeah. Yes, correct. Yeah, it's symmetric, right? Because Q1 times Q2 or Q2 times Q2. Okay. So more on units. I want to talk more on units. So we said here, charge is, potential 1, 2 is Q2 V1, right? So more on units. Suppose Q2 is equal to 1E, which is 1.6 times 10 to the minus 10 coulombs, right? And V1 is 1 volt, which is 1 joule per coulomb. Then the potential energy between them, U1, 2, is going to be what? Q2 times V1, right? What is Q2? 1E, right? Which is this one. So I'm going to write 1E. And then V1 is 1 volt, 1 V, 1 volt. So it becomes 1 EV. It's called an electron volt. So if you multiply them, little e is this, 1.6 times 10 to the minus 19 times 1 joule per coulomb, you get 1.6 times 10 to the minus 19 joules. So 1 electron volt, this new unit called an electron volt, is related to joules by this. This is the conversion. I asked my previous class if anybody was taking chemistry, only one person, and they did not remember the ground state of hydrogen. Do you remember what it was? Does anybody remember it in electron volts? I don't know if it's not electron. No. Did they mention it in joule maybe? No. Okay. So something like I think it's minus 13.6 electron volts or something like that. Anyways, okay. I thought you have seen it in chemistry. So if you see the unit electron volt, it just means this. It's this magnitude. It's a tiny unit. And it's an appropriate unit for atoms because you don't want to always have small or big factors. Just like I mentioned, like if, from here to LA is like about 400 miles. You don't want to measure it in yards or feet. You don't want to see it say, I don't know how many feet that is, thousands and thousands. You want to measure it with some unit that's appropriate. Just like you don't want to measure from here to the exam is 168 hours. You just want to say 7 days, right? Yes?
I guess this is more of a conceptual question, but at least the potential energy being associated with the conservative force like you said, but in this case, the electric potential energy is related to both electric potential, which doesn't come from a force at all, so it's not integral, we only have the field and the displacement. Is that possible? Like, can a potential
Well,
energy flow?
let's say I have a conservative force and you divide it by 2. Is it still conservative? Yeah. It does not. You haven't changed its mathematical form, right? So here, the electric field is still the force divided by some constant, which is the charge, right? So it's still conservative.
Okay.
It's what is conservative is that 1 over r squared. That remains for the field and the force. Yeah. So if you have a force, like a vector field, and it's a conservative vector field, twice that vector field is still a conservative vector field. If you're in Calc 3 right now, you will cover conservative vector fields. They will tell you how you know that they are conservative. Yeah. We will skip that part in here. Okay. So I think I've talked about all the units I need to talk about. That's good. Yeah. Time flies. So the next thing I want to just emphasize some conceptual stuff. Okay, some conceptual stuff. There are things that happen with electricity that you have not seen with masses. And the reason is this. Here's a mass. This is a mass. If I move the mass in the same direction as the gravitational field, in what direction is the gravitational field? Downward. So if the mass is moved in the same direction as the gravitational field, what happens to the gravitational potential energy? Increase or decrease? Decrease. It will decrease. So if you move in the same direction as the field, your potential energy decreases. And that's it for masses. And the reason is we don't have something called a negative mass. All masses are positive. Okay? All masses are plus. For charges, on the other hand, we have positive charges, and it will work the same way as masses, just the way you would expect it. But you got some negative charges, and it will just be the reverse. Okay? So here's how I'm going to introduce that. So imagine this wall is positively charged, and this wall is negatively charged. Say it's an infinite sheet there, infinite sheet here. In what direction is the field? Right. That one. Yes, this one. Is it uniform? Meaning constant, same direction. Yeah, it's a uniform field, right? Sigma over epsilon naught, right? If you have infinite sheets. So between the two sheets, it's a uniform field. Okay. So let's say I have let's use that. I have let's say the green chalk is a positive charge. If I bring the chalk closer to the positively charged wall, will it have more potential energy? Yes, because if I just let it go, what happens? It will just spring this way. So it has the highest potential energy when it's there. How about here, when I bring it here? And then maybe make it touch the wall. So it has lower, in fact, the potential energy here is the lowest. Right? It's where it wants to be. It will not move. It will just stay there. Yeah, it will be 0. We'll talk about plates in a moment, but conceptually that's what's going on. On the other hand, let me get some orange chalk or red, This is a minus charge. This is negative. Okay. So now, this is negative. Will the negative charge have more energy here when it's
Yeah.
close to the negative wall?
Yeah.
Yeah, because what happens when I let go of it? The minuses repel it, the pluses attract it, so it will just go that way. So the red, this minus charge has the lowest potential energy there, and it has the highest potential energy there. Versus the green charge was, yeah, it had the opposite. It had the opposite because it's plus and minus. We don't encounter that with masses. You don't have a negative mass. Okay, so in other words, for a positive charge, in what direction is the electric field again?
Right.
Here? Yeah, that way. For a positive charge, if you move in the same direction as the field, the potential energy decreases. If you move opposite to the field, the potential energy increases. Similar to the mass. If I raise a mass, I'm moving opposite to the field, right? Gravity is down. If you move opposite to gravity, the potential energy increases. And if you move in the same direction as gravity, the potential energy decreases. For negative charge, it's just the opposite. It has a minus sign. We don't have it with masses, but we do have it with charges. So here is a field. Let's say here is our field. It's this way. Say it's a uniform field. E. It's just some number E and then I hat. And here is I hat, here is J hat. I hat, that's the J hat direction. So it's a uniform field that points that way, that direction. And we want to know what's the change in electric potential as we move from here, let's say to here. So let's say I have my charge Q from here, and then we move it to here. This is X initial, this is X final. Charge is moved that way. So who can tell me the displacement in this case? What is dr in this case? What did you say?
dr
Something
I
I hat. Yeah, dr I hat. Yeah, I like that. Or we can call it dx I hat because it's in the x direction. Yeah, yeah. dx dr I hat. So my change in potential delta V by definition is minus that integral, right? It's minus like this, from R initial to R final of E dot dr. I'm going to do this just once because for this types it will just be basically electric field times distance. That's what it's going to be when the electric field is uniform. So let's see what we get. We have minus, what's the dot product? E I hat dotted with dx I hat. What does it become? EDX. Good. So I get EDX. Integrated between R initial to R final. Our electric field is uniform, right? It's constant, so you can pull it out. So we get delta V will equal to minus E, and then, this should say X initial, X final. So it would be X final minus X initial, which is delta X, right? Delta X. So if delta X is positive, then the change in potential would be negative, right? So if you move in the same direction as the field, your potential change is negative. I hope that's clear. This is what this is saying to us. I just, earlier I demonstrated with my hands and with chalk, but here with math. I just showed you. Hope that's conceptually clear. So the potential, I talked about potential energy and potential. The potential decreases if you move in the same direction as the field. The potential energy, the change in potential energy, U, look, potential energy is charge times field, right? Times potential. Potential energy, charge times potential, right? So the potential energy would be the charge times the potential. So it's going to be this Q times the change in potential. In this case, it's going to be Q times the change in potential. And notice, if the change in potential is positive and Q is positive, then the change in potential energy will be what? Positive. If the change in potential is positive, but Q happens to be negative, then the change in potential energy is negative. So but we never encountered that with masses, because all masses are always positive. We didn't have masses with a minus sign. But charges, you can have plus or minus. All right. Let's go to, let's do an example of this one. This next one. Can I erase those two boards over there? Yes. Let's say let's say now our electric field is this way. Just for a change, I reverse the lines. The electric field is to the left. Let's say I have if we move this way from here to here, this is initial and this is final. Is the change going to be delta V? Is delta V going to be positive or negative? From initial to final. Positive because?
Oh wait, we haven't determined whether the left side is negative or positive.
The electric field is to the left.
We're going from I to F,
Yeah, initial to final.
so it's negative, positive.
What's the so is the electric potential?
Oh, it's negative.
Is delta V positive, negative, or zero?
Positive.
Positive because?
Electric field is left and
Yeah,
sway
yeah.
towards the right.
Okay, so you move against the field.
Yeah.
If you move against the field, it's positive. The change in potential is positive. I think we said it here. If you move with the field, the potential will be change will be negative. And if you move against the field, the change in potential will be positive. Okay? So in this case, we're going against the field. So the change in potential will in fact be positive. Suppose then the change in potential will be 100 volts. Okay? The change in potential will be 100 volts. Just trying to say this is why it's positive. Let's say we have an electron at that point, not an electron, a proton at that point, moving at a certain speed. Let's say we have a proton, which is positive proton. Moving at a certain speed, V equals to V is equal to 5 times 10 to the, no, 2 times 10 to the 5th. 2 times 10 to the 5 meters per second. And so the question here, when it gets to here, what's the final speed? Final speed. And we know the charge of a proton and the mass of a proton. We can look them up. Suppose they're given to us, so we can always, or we can always look. So what can I? So we're asked, when the proton moves this way, what's the final speed? So before we answer the question, is the proton going to slow down or speed up? Slow down because it's going against the field, right? So again, in this case, the field is this way. So which wall is positive? That wall is positive. This wall is negative. So if you have your proton, it's positive. It's approaching the positive wall, so it should slow down, right? So it should. The speed here should be less than 2 times 10 to the 5. Whatever it is, it should be less. So that's intuitively, we already know. So what should we do? Conservation of energy. Conservation of energy, you can say the change in kinetic energy plus the change in potential energy is equal to 0. Right? K final plus K initial. You can write your conservation of energy. Yes, we did this one earlier. So delta K is equal to delta U. So delta K is equal to minus delta U over to the other side. Delta K is equal to minus. How is the change in potential energy related to the change in potential? Q times the change in potential. Right? So it is the charge times the change in potential. This one is V now. What is the charge? It's a proton. So what's the charge? 1.6 times 10 to the minus 19, which I will call E for now. Yeah, so it's E times delta V. That's the symbol. That's the charge of the proton. Delta K is 1/2 mv final squared, 1 minus 1/2 mv initial squared. Move this to the other side, so you get, and then multiply by 2 and divide by m, so you get v final squared will be v initial squared minus 2e over m times delta v, right? Multiplied by 2 divided by m, and move this to the other side. Next, we're going to square root both sides, solve for v. So you get v final will equal to v initial squared minus 2e over m delta v. The mass of a proton, we can look it up, or it will be given to us. 1.67, right? Times 10 to what power? What's the mass of a proton? 1.67 times 10 minus electron is 31. 27. And then the voltage is 100. Delta V is 100. Okay. Yeah. So it would be less. So it would be a number that's less. Let's look up how much less. Not too much. But 1.44 times 10 to the 5th. It's a speed, so meters per second. I want to summarize what I did today, kind of, just to make sure that we're clear. We talked about point charges. Point charges. So this is a summary of what we did kind of today, right? I'm not gonna go through the integration and stuff like that, but if we have two charges, Q1 and Q2, and they're separated by a distance R, then the potential energy between 1 and 2 is equal to K Q1 Q2 over R. K is 1 over 4 pi epsilon. If I have a charge Q1, let's say, and I'm at the distance R, this is called what? Electric potential or potential energy? This one is energy, yeah, potential energy. For potential, electric potential, it's the V. Let's say this one is Q1, we say V1 is equal to K, what? Q1 over R. Right? And then, so you will notice here, if you look at these two, you will notice that U12 is equal to Q2 times the potential that if you place Q2 in potential V1, you will get that's the potential. Potential is just everything that the potential energy has except for the second charge. We should also notice that if we use the change in potential energy is the charge times the change in potential. That's for point charges. For uniform fields, again, how do you produce a uniform field? By 1 point charge? No. You need sheets of charges, right? So it's not due to 1 point charge, so they're due to many charges. And so for uniform fields, let's say if the field is in this direction, and it's uniform, and this is the initial, and this is the final, go like that. And this distance this way is delta x, right? Then delta V is equal to minus E times delta x. If you move in the direction of the field, the potential decreases. If you move against the field, the potential increases. Yes?
This is only for a positive charge, right?
There is no mention of charge here. Yeah, right?
But
This is just the potential.
but the sentence you said with regard to moving with the field versus against it only applies to one part. The equation itself is for both.
This one, okay, so for the, that is, the potential always increases if you move against the field, and it decreases if you move with the field. The potential energy, delta U, if it's a positive charge, it will increase against the field. If you move against the field, it will decrease if you move in the direction of the field. If it's a negative charge, the potential energy increases if you move with the field. It's just the reverse.